Okay, we are on streaming right now. So good morning, everyone. We will start the exam of Ariel Sanhueza Román, who is opting to the degree of Master in Informatics Sciences, with the thesis entitled A Limited-memory Levenberg-Marquardt Algorithm for Solving Large-Scale Nonlinear Least Square Problems. The committee exam is formed by the following professors: external co-referent Professor Timothy Sauer, and the internal co-referent myself, Professor Marcelo Mendoza, and the advisor of the thesis, Professor Claudio Torres. The exam has three parts. The first part is the presentation of the work made by Ariel Sanhueza. The second part includes the questions and comments from the committee exam, and the third part is the qualification of the exam. So Ariel will have about 35 minutes, 40 minutes to present the work, and then we will go on the second part of the exam with the questions from the committee. So Ariel, you can start the presentation.
Okay, welcome everyone. Thanks for attending. My name is Ariel Sanhueza, and today I'm going to present my thesis topic, which is called A Limited-memory Levenberg-Marquardt Algorithm for Solving Large-Scale Nonlinear Least Square Problems. For the structure of this presentation, first I'm going to start by making an introduction to set the problem and the main objective of this thesis. Then the numerical nonlinear solver is going to be presented with the two main contributions of this work, the NS LSQL method and the quantized approximation of a matrix. Then the more relevant numerical experiment will be shown, and finally the conclusion of this work. So, some examples of nonlinear problems arise in different fields of science, for example, in physical, chemical, and biological models, usually through partial differential equations. Another example is in machine learning model, that the models are defined by a nonlinear function, and another example is in nonlinear regression of data. So in some cases, this numerical solution of nonlinear problems can be approached as a system of nonlinear equation when the equations are discretized. So a nonlinear system of equation is defined by the equation 1, which is the problem to find a vector x such that this f function equals 0. This function f is defined as m function, each one receiving an input vector of size m. When m is greater than n, we call it an overdeterminate problem, which is the main focus of this thesis. So an approach for solving this kind of problems, we can define a function g as the residual of the function f, and then solve the unconstrained minimization problem posed by the equation 2 of minimizing this function g. So classic methods works pretty well for small to medium scale problems. However, for large scale problems, computational issues appears related, for example, to memory constraints and computational cost of the procedures. To give an example, most of unconstrained optimization methods usually requires the gradient of the objective function, which in this case is the function g. This gradient is defined as the product between the transpose of the Jacobian matrix of f and the vector f. If we are solving a large-scale problem, this Jacobian matrix has a large size, and it requires a prohibitive amount of memory for storage. To give an example of this, if we see this plot where the x-axis denotes the execution time of an algorithm and the y-axis denotes the memory consumption of this algorithm, we have two execution here. One is an algorithm with an explicitly stored matrix, and the orange marker denotes a matrix-free variant of these algorithms. So here we have the contrast between the memory consumption and the execution time. In this case, we were capable of building and storing this matrix explicitly, because the problem is relatively small. In this case, the memory used approximately 12 gigabytes of memory. But if we are solving a larger problem, we cannot store the matrix in this case, and we only have the option of solving the problem through a matrix-free approach, which in this case will require even more execution time. If we see this table with different methods for solving nonlinear problems, and some of them in the large-scale variants, we see that the columns of requirements, most of all of them requires the Jacobian matrix or the gradient function as a requirement of the method. If we see the row with the GFNK method, which is the Jacobian free Newton-Krylov method, a matrix-free variant of the Newton method, we see that it do not require the Jacobian matrix because it's a matrix-free method, but we are restricted to the case when m equals n, which is not the case for overdetermined problem. So given this context, the general objective of this thesis is to design a nonlinear solver capable of handling large-scale overdetermined nonlinear system of equations. To achieve this general objective, we define three specific objectives. First, to design a feasible approach for computing the Jacobian matrix of a function f, build a linear least square solver capable of handling a large-scale problem in the given described context. This will be explained in more details later. And finally, a more practical objective is to design a parallel implementation of the proposed algorithm. So we know that the problem that is decided to solve is given by the equation 3, which is solve this nonlinear system of equation. So if we define the function g as the residual of the function f, then we can solve the unconstrained optimization problem given by minimizing this function g. In this thesis, we use the Levenberg-Marquardt method for solving this problem. The method is solve the problem iteratively, as given by the equation 4, starting from an initial guess, where this value with this step delta x sub I is computed by solving the linear least system of equations, given by the equation 5. If we know, a remark here is that this matrix is symmetric positive definite, so its inverse exists as long as the lambda I sub value is greater than 0. Some efficient solvers to solve these problems are, for example, the Cholesky decomposition or the conjugate gradient methods. As I said before, for large-scale problem, the computational storage of in this case, the Jacobian matrix, pose an issue due to its prohibited amount of memory required. So instead of solving the previous system of equation, which is, we can solve this equivalent problem given by the least square problem, regularized least square problem, given in the equation 6, which is also equivalent to the unregularized linear least square problem in the equation 7. In this case, the previous system of linear equation is the normal equation of these two least square problems. So an algorithm for solving these kinds of least square problems is the LSQL method, which is mainly used for large and sparse problems. It is mathematically equivalent to the use of the conjugate gradient methods over the normal equation, but usually LSQL is more numerically stable. So LSQL can solve this least square problem in a matrix-free way if we give to the method two procedures. First, a routine to compute the product between the transpose of the Jacobian matrix and an arbitrary vector v, and a procedure to compute the transpose of the Jacobian matrix times an arbitrary vector. For the first requirement, the product between the transpose of the Jacobian matrix and a vector v, we can use the same approach that is used in the GFNK method, which is a finite difference approximation. For example, the expression 8 gives a second-order approximation for the product between the Jacobian matrix and a vector using only function evaluation. It does not require the Jacobian matrix, only use the function f to approximate the decided product. In this case, the approximation is based on a central difference schema. However, a low-cost approximation for the product between the transpose of the Jacobian matrix and a vector is not known, and matrix-free alternative demands a high computational effort. So given this issue, in this thesis, two methods are proposed and combined with the Levenberg-Marquardt method to handle large-scale problem. First, the NS-LSQL method, which is a modification of the LSQL method and requires two procedures. First, a routine to compute the product between the transpose of the Jacobian matrix and a vector, which in our case we use a finite difference approximation, and any routine that is capable of computing some approximation for the product of the transpose of the Jacobian matrix and a vector W. The second method proposed is to approximate the transpose of the Jacobian matrix using a quantized approximation. The idea here is to compute a low memory approximation for the required matrix. So to start first, to explain the NS-LSQL method, we will briefly explain the LSQL method. So let's consider that we want to solve the following unregularized least square problem given by the equation 9. In this case, the LSQL method is based on the bidiagonalization process of Golub and Kahan, which is given in the equation 10 and 11. In this case, the matrix B sub k and B sub k plus 1 are lower and upper bidiagonal matrices, and the matrices U sub k and V sub k are orthonormal matrices. So these two recurrence stars using the following two vectors, and this is very important because if we solve the least square problem restricting the solution of the least square problem to the column space of V sub k, then we have the equality given by the equation 12 that it's used to reduce the original least square problem into a smaller one defined by the equation 13. In this case, the new problem, the problem in the equation 13, is an k plus 1 times k least square problem compared to the original one, which is of size m times n, in this case, in the case for the matrix J. So, to start describing the NS-LSQL method, let's suppose that we do not have the transpose of the Jacobian matrix, only a constrained memory approximation, which we denote as J tilde, with an unknown accuracy. Since we do not have the Jacobian matrix, also recall that from the Levenberg-Marquardt context, we only have the function f. So we may approximate the product between the matrix J times V using a finite difference approximation, and approximate the product between the transpose of the Jacobian matrix and a vector using this constrained memory approximation. However, if we use this J tilde, the recurrence in LSQL are no longer valid. So, if we see the first recurrence given by the equation 14, this is mainly used for two purposes. First, to obtain the matrix B sub k, which is used in the smaller least square problem, and to compute the next vector U sub k plus 1. In this case, this expression is not affected by the usage of the the restricted memory approximation. However, the second recurrence, which is given by the equation 15, is used to obtain the next vector B sub k plus 1, which is used to restrict the least square solution. And in this case, this equation or this expression is affected by the usage of this constrained memory approximation. So, since we are modifying the value of B sub k plus 1, then the usage of this matrix J tilde modifies the values of the vector, and thus the space from where the solution is going to be computed in each iteration. However, an important observation is if the vector V sub k plus 1 is still a linearly independent vector against the previous V sub k vectors, then it's still a valid vector for the search space. And this observation is the main idea of the NS-LSQL method. So here we have the NS-LSQL equivalent recurrences that are computed using replacing the instances of the transpose of the Jacobian matrix by its restricted memory approximation. An important remark here is that the the NS LSQL version of the matrix B sub k and B sub k plus 1, which in this case is B tilde sub k and B overlying B sub k plus 1, are upper Heisenberg matrix and upper triangular compared to the LSQL versions that are bidiagonal. The next steps follow the same idea than in LSQL. Using these recurrences, we can build a smaller least square solver that is solved at each iteration and is given by the equation 16. In this case, as I said before, the matrix B tilde sub k is upper Heisenberg matrix and is of size k plus 1 times k. Some important considerations about NS LSQL methods. The inner least square solver, the smaller one, can be solved efficiently using accurate decomposition. Also, we must note that the matrices V sub k and U sub k are usually dense and its size increases at each iteration. So a restart approach is required to avoid the increase of memory of the method. Also, an important convergence property is that the solution computed at each iteration of the NS LSQL method decrease monotonically the residual of the least square problem, which is a decided property in a least square solver. So, at this point, we have a method to solve a large-scale least square problem, but we haven't defined how we can compute this constrained memory approximation. In this section, I'm going to briefly explain a proposal to compute this constrained memory approximation, which is based on a quantization technique. Quantization is a lossy compression method that, in general, is a technique that maps a large set of values into a smaller set. In particular, our approach is to map scalars into a regularly divided set that includes the zero value. So to approximate a vector, we quantize each of its coefficients individually. Then a matrix is just quantized column by column. The general idea of our quantization method is given a vector p that we want to quantize and a number of b bits to use for the quantized approximation. Our method generates 2 to b minus 1 values between minus p and p, including both values, where in this case the value of p is the larger value of the vector p in absolute value. So the idea here is that each coefficient in the vector is approximated by its closer value in the generated set of values. For example, in this plot we have the results of quantizing using this approach a uniformly distributed vector in the range of minus 10 to 10 using only 3 bits. In the x-axis we have the values of the input vector, and in the y-axis we have the quantized value after applying this quantization technique. So we see that the number of values, in this case, from the original range are mapped into 7 possible values. So the observation here is, since we have a total of 2 to b minus 1 possible values in the output sets, then we require only b bits to store this number. In our implementation, the used expression to approximate each coefficient in the input vector v is given by the equation 17, where the more important part is that this value y sub I tilde is obtained by rounding the value of y sub I to its nearest integer. So the approximation comes from the part of rounding this value. So, as I said before, to approximate a matrix using this quantization technique is to quantize each of its columns, and the expression that is used to represent the approximation is given by the equation 18, where in this case the matrix M sub V contains the integers resulting from rounding, and the matrix D sub B is a diagonal matrix containing these scalar values D sub I. An important, well, if we compare to a double precision matrix, which is the common precision used in numerical solver, if we use B a number of B bits less than 64, then we are achieving some rate of compression. Also, in our implementation, we use the concept of layers to approximate a single matrix. A layer here is just the concept of layers is a sum is a sum of quantized matrices to approximate a matrix A. In general, the ith layer is computed by quantizing the matrix of A minus all the previous quantized matrices. So we quantize the error of the current approximation. The idea of this concept of layers comes from the following theorem, which says that let P be a vector and P tilde be its quantized approximation, then the norm of the error produced by this approximation is less than the norm of the vector P for all B greater or equal than 2. The idea here is that, for example, if we quantize a vector P by a quantized vector P sub 1, then the norm of this error is less than the norm of the previous vector. Now we can compute a second approximation P sub 2 from the previous error, and this norm is less than the previous norm. So if we change this procedure, if we make this procedure at each iteration, we are decreasing the norm of the error. And this is the idea of this concept of layer or sum of quantized matrices. Important observation, the method to quantize a matrix, we approximate it column by column. So in the case of the Jacobian matrix, that is the objective of this procedure, we can use a finite difference approximation with the canonical vectors to obtain the columns of the Jacobian matrix. Also, remember that we want the product between the transpose of the quantized approximation and a vector, and this can be computed using the expression in the equation 19, which is obtained transposing the previous expression for the quantized matrix. Also, an important remark here is that it's more explained in detail in the manuscript, and we can discuss it at the end of the presentation. But in modern computer, there exists a minimal unity of storage, which is usually 8 bits or 1 byte. So to store coefficients using less than this value, for example, 5 bits, we require a specific data structure to compress the data to achieve this required memory usage. So to perform the matrix vector product, we also require a decompression routine to decompress the data that was stored in this data structure. Now I'm going to give the more relevant numerical experiments. The more relevant experiments that were performed are the following ones. First, we test the accuracy of the quantized approximation. We also test the performance of the NS-LSQL method against the original LSQL method. We also test the memory usage of the NS-LSQL method against the LSQL method, which is a very important test because we expect that the NS-LSQL method is capable of solving the problem using less memory compared to the LSQL method. And finally, we test the performance of the LM-NS-LSQL method, which is the name that to describe or denote the combination of the Levenberg-Marquardt solver with the NS-LSQL method. As test problem, we use 6 test problems for our experiments. 2 of them are linear ones, and the remaining 4 are 4 nonlinear problems. For the dimension of each test problem, we use approximately, or the dimension was selected to use approximately 32 gigabytes of memory if the Jacobian matrix were to be explicitly stored. This never happens in our experiments, but if we have computed this Jacobian matrix, it will have used 32 gigabytes of memory. So the first experiments measure the error produced by this quantized approximation. In this case, we compute the relative error of the quantized approximation for a particular configuration of layers and bits, and the Jacobian matrix compute by finite difference in the Frobenius norm. The results are in the following plots. In this case, the x-axis denotes the memory used by some configuration of the quantized matrix, and the y-axis denotes the relative error. These purple dashed lines denote the 32 gigabytes of memory that double precision matrix use if is stored explicitly. Each marker in the plot denotes the result of on a particular number of layers for some number of bits. For example, the first green marker denotes the error computed using one layer of 6 bits. The second marker denotes the error of 2 layers of 6 bits, and so on. So the main conclusion here is that in general, the quantized approximation, even though it's very simple in description, may produce small errors compared to considering that we are using much less memory than the fully double precision matrix. In fact, errors around 10 to minus 6 are obtained using only 1/3 of the fully double precision matrix. Also, as expected, using more layers and more bits per layer improves the approximation or decrease the error of the approximation. Of course, how the error decrease depends heavily on the problem. For example, in the modified trigonometric function, using 3 layers of any combination of bits produce more or less the same error. However, adding a 4th layer improves if this new layer contains more bits. The second experiment is the usage of this quantized approximation in the context of the transpose of the matrix vector product. As a reference vector, we use a matrix-free approximation given by this equation, which in this case, the product between the Jacobian matrix and the canonical vector A sub I is computed by find difference. And in this case, we also measure the relative error between this reference vector and the product between the quantized approximation and a vector. The results are in these plots. The same tendency of the previous results are maintained. Also, if it's verified that using also more layers or more bits per layer decrease the error of the approximation. Also, another conclusion is that the matrix performs or the error is relatively small for the quantized approximation, then the error of the matrix vector product is also relatively small. So the experiments are more or less related to the previous sets of experiments. Now that we know how the quantized approximation performs, in this experiment we test the NS LSQL method against the LSQL method, but using different quantized matrices, all of them having the same total amount of bits per elements. For the LSQL case, we use the matrix-free approximation for the product of the transpose of the Jacobian matrix and a vector. In the case of all experiment, we solve a least square problem, a regularized least square problem, for a uniformly distributed random vector x sub I. These are the more relevant results. An important conclusion here is that the NS LSQL method performs very similarly in the sense of the relative residual achieved compared to the LSQL version. Although in some cases, like in the modified trigonometric function, where in the early iteration we see that in some quantized configurations there is a minor difference between the LSQL execution and the NS LSQL version, this difference tends to be smaller when the iteration progresses, and in all the case, all methods converge to almost the same relative residual. So the conclusion here, if we choose the parameters carefully for the quantized matrix, we may obtain a very similar performance in the NS LSQL method compared to the LSQL matrix-free version of the method. Now, the following experiment will also test the NS-LSQL method against the LSQL method, but using a quantized matrix with different number of bits. In particular, we will use low bits quantized matrix with low bits usage. The idea here is to visualize how this low bits usage for the quantized matrix affect the performance of the NS-LSQL method, and the results are very conclusive. If we see the first plot, the normal problem, we see that the case when using NS-LSQL method with a quantized matrix of one layer of 2 bits produce a very early saturation of the residual and produce a very slow convergence. As expected, if we increase the number of layers or bits per layer, the decrease or the residual decrease gets more closer to the performance obtained by the LSQL matrix-free method. But the conclusion here, if using a quantized matrix that use too few bits, we have the risk of obtaining this early saturation of the residual that is also obtained in the quadratic function and the diagonal function, and thus slowing considerably the convergence of the method. The next experiment tests the memory usage of the LSQL method and the NS-LSQL method and the execution time also. Here, the configuration used were first LSQL was used with 2 configurations. First, with an explicitly computed Jacobian matrix in a double precision, and a matrix-free version of LSQL for the products of the matrix, the transpose of the Jacobian matrix times a vector. For the NS-LSQL method, we use different combination of bits. The results are in the following plot. We see that, as expected, the LSQL method using an explicitly stored Jacobian matrix performed faster than the rest of the methods, but also use the larger amount of memory. On the contrary, the matrix-free version of the LSQL use much less memory than the rest of the method, but its execution time is much larger than the rest of the methods. Between them are the more of the cases of the NS-LSQL method, with the exception of the combination of 32 bits per coefficients. In this case, takes much time because we are using this compression and decompression routine to obtain the matrix vector product, and this adds an overhead to the method. However, if we using the previous results of the experiments, we see that, for example, using an 8 bits combination is much faster than a matrix-free version of the LSQL, and also use much less memory than an explicitly Jacobian matrix with LSQL. An option could be to use, for example, 2 bits, which is much faster and use much less memory than all the previous methods. But as we conclude from previous experiment, we have the risk of obtaining an early saturation of the residual and taking much longer time to achieve a specific residual value. Finally, the last numerical experiment is to test the performance of the LM-NS-LSQL method to solve a nonlinear problem. In this case, we use only one configuration for the quantized matrix that was chosen based on the previous results, which is 2 layers of 3 bits and 1 layer of 2 bits. The results are summarized in the following plots. For the first 2 problems, the normal problem and the modifier trigonometric function, these 2 problems are 0 residual problems, and as we see, we solve it up to the tolerance. And the last 2 problems, the quadratic function and the diagonal function, which are not 0 residual problems, we achieve convergence to a local minima for both problems. So the conclusion of this work, first, we successfully developed a method for solving large-scale over-determinate nonlinear system of equation, which is the general objective of this thesis. Also, a linear least square solver was presented and implemented, and also is capable of handling large-scale problems in the context of the Levenberg-Marquardt solver, which is having only the function f to approximate the required matrices. Also, one of the main contributions of this work is the proposal of a robust matrix approximation strategy. The numerical experiment showed that the approximation can obtain very small error even using a small number of bits depending on the matrix. Of course, this depends heavily on the problem. But in our tests, using, for example, 8 bits, which is 8 times less than a double precision matrix, obtain very good results considering the saving in memory. And finally, the performance of the NS LSQL combined with the quantized matrix was very competitive compared to the LSQL1, considering the memory that the NS LSQL method used compared to, for example, a double precision matrix in LSQL, and it's much faster than using a matrix-free variant of the LSQL method. Well, thanks for your attendance and attention. Now we have time to answer the possible question that you may have. Thanks to the committee.
Thank you, Ariel, for your presentation. It was very clear. So we will go now to the second part of the exam. That is the part of the questions of the committee. So we will start with Professor Timothy Sauer. Please, Professor.
Okay, well, I have many questions. I'll try to limit my time, but let me start with some very a couple technical questions, and then I'll zoom out and ask some more general ones. So I'm curious. I'd like to hear a little bit more about in the insides of the NS-LSQR algorithm you're talking about, where you made the J tilde and the U tilde and V tilde. You mentioned that a restarter, you might have to do some restarts because the U tilde and V tilde would grow in size.
Yeah. Well, this is something that is not required at the beginning in the LSQL method, because since the matrices are bidiagonal, the amount of memory that they require is much less. And in fact, for example, if we use a Gram-Schmidt orthogonalization, it requires only 2 vectors. In the case of the NS LSQL method, is more closely related, for example, to a GIMRES method, which requires all the previous orthonormalized vectors. Although the restarting approach is more a saving or is more a safeguard method for avoiding the continuously increase of memory, in all of our experiments, the restarted was not necessary. We achieved a convergence before applying the restarting approach, but it's more a safeguard method rather than it's more as a method to avoid the high memory consumption of the dense matrices.
So in other words, yeah, you don't want to store all of those previous vectors that are from the orthogonalization. So you restart and start over, I guess, at some point if you run out of memory. Is that the idea?
Yeah. We use the current solution of the least square problem as the new initial guess, and we restart all the algorithm all again.
Okay. I had a question about your the accuracy plots you were showing at the end. Were you showing, I guess I conclude that you were showing us the error of the least squares solution, not the residual in most of those plots. At the very end, at the very end, you showed a residual plot. Yes. Okay. Yeah. I just wanted to make sure I knew what I was seeing there.
Yeah. This one. Yeah.
Yes, that one was a residual. Before that, it was just the error of the unique least squares solution, I believe.
Yeah, the inner least square that is solved at each iteration of the Levenberg-Marquardt method. This is the residual of the nonlinear least square problem.
Yes. Okay, if you back up actually to slide 48, you get some nice asymptotic slopes here, right there. So do you have explanations for the slopes, for the various, in terms of the number of bits? That would be kind of interesting. Can you analytically explain the slope?
Yeah, it's a very good question. We haven't started the result, although these slopes are obtained more in the randomly in the random, in this case, the normal problem and uniform problems are linear problems that comes from a uniform and normal distribution. But in the cases of nonlinear problem, the slope is not too clear. So,
well, yeah. So maybe maybe it's a power law or something like that. That's a little less. That's not a, I mean, this would be this would be an exponential method.
Yeah.
Maybe if you graphed it on a log plot, C and D, you might see you might see an actual slope, and then numerical analysts really want to know what the convergence rate is, and maybe you could explain it analytically. What you're seeing
it's a very interesting question to answer, in fact.
Yeah, that would be, I mean, I assume you're going to publish this someplace, because I think this is really interesting work. So, and that's something that you may, the referees might ask you. So I'm just throwing that out there. So I don't know much about this whole idea of quantizing matrices. It's really cool. And I think there's, I guess some people are working on this kind of thing. In fact, one could consider everything you do in numerical linear algebra, this is just one small piece of it, doing it in a quantized manner for matrices that don't fit in your memory. So I'm kind of asking you, what is the, what is the literature about this? And how does your method, which I think is kind of new, this layered approach to doing quantization, how does it compare to what other people are doing in quantizing matrices and then doing various numerical linear algebra methods, if you know?
Yeah, in fact, the quantization approach or the quantization techniques is not new. It has been studied for a lot of years, but in the context of quantizing a matrix for a numerical solver, it has not been used. It's used in another context. For example, in some electrical, in fact, comes from the electrical fields. It's used currently in computer science to, in fact, I got the inspiration of using this in this context for in machine learning is used to reduce the model size. So the weights of neural networks are quantized, and then the memory required of these neural networks, it's much less than the original in double precision. So I got the idea from that, or a combination of other things, but it's not. It's very surprising that even having this performance, which is I consider that it performs really well compared to the memory savings. It's a surprise that has not been used in numerical solver. Usually, the solver expect the true Jacobian or the true transpose matrix, not a quantization. I have seen other types of usage. For example, there are works that use, for example, an stochastic distribution of the accuracy for the matrix, for example, but not the quantization itself. So in this context, in numerical linear algebra, it's not very popular, the idea, and I consider it's a very good approach for handling large-scale problems. And in fact, I say in the conclusion, I said that is one of the main contributions because it's not tied to, for example, the LSQL method can be used in other solvers, for example, linear ones, nonlinear ones. It's very independent from the Levenberg-Marquardt methods. So it's a contribution by itself.
Yeah, that's exactly what I was getting at. I mean, even for matrix factorizations, for matrices that don't fit in memory, maybe this would be an interesting approach. So I think there's a lot of, a lot of directions you could go with this, because I think, especially the layering idea you have here is very interesting. And so it might be very useful for huge problems that don't fit in memory. And, problems, there's no limit to the size of problems that people care about nowadays. But yeah, I understand that it's used a lot now in machine learning. And in fact, there are compilers now, that do half precision and quarter precision and all of these things. It's related to what you're doing. Maybe one more question then. I don't want to monopolize the conversation, but all of your examples here are synthetic examples. Where do you think in your, can you guess about where in applications this idea of this better Levenberg-Marquardt method might find a good usage? Have you thought about that?
Well, Levenberg-Marquardt method is used in some contexts. Maybe the most popular ones is used in, for example, in the machine learning training of models, because since it converts fast. For this approach or for this property it's preferred, for example, over the descent gradient or the gradient descent optimization. But since it's required a matrix, it's not used in large problems. It's used in smaller problems, especially in machine learning that usually problems are very large, or we have many samples, and especially in the neural networks. Another popular example is in probably one of the most popular example of nonlinear least square regression of data is in the forecasting and weather prediction models. There is a model called 4DVAR or 4DVAR,
Yes.
which use a nonlinear regression of data. And usually, in this case, we also have many samples, but for memory constraint, usually use much less data to make this regression. So this, I think it's a very interesting idea to test the overall method in these cases, especially in the latest one, the forecasting prediction.
Mm-hmm. Yeah, very good. Yeah, that's a high number of equations situation for sure. Yeah. Okay, thank you.
Thank you, Professor.
Thanks.
Now it is my turn. Ariel, I don't know if you have the thesis at hand to see the pages, because my questions are related to the document, not to the presentation. So
if you give me a couple of minutes, I can open it.
Okay. But in general terms, I will start with a more general question. So you say in your document that the page number 21.
21.
Okay. I will read some a part with an affirmation, and then I will ask to you to justify the sentence. So you say that related to LSQR, that whose memory requirements increase quadratically along with the number of iterations. So this increased use of memory can be handled with a restart strategy.
Yeah.
So as traditionally used in Krylov subspace-based methods.
Yeah.
Could you please comment on this affirmation? What do you think that this is a good property, or it could be useful for your approach?
It's very related with the question that Mr. Sauer asked. It increased quadratically because we are handling matrices. So one additional iteration means a new row and a new column for the matrix that is going to be stored. The restarting approach is used, usually all Krylov subspace method has a restart parameter. For example, in GMRES, in LSQL, we can use also a restarting approach. Usually in that cases, the convergence is usually difficult to assess in the case when using restarting. In this case also may affect the convergence, but the idea here is that if the signs, of course, the idea here is that using, for example, the quantized approximation, we are having memory savings, so we can push a little more the NS LSQL method compared, for example, to a GMRES with a large scale matrix that the memory range that we can move is much smaller. And of course, if we reach the limit of the memory, the method cannot continue its iteration because we need to increase the memory of, in this case, the U and the V matrix. So the idea of restarting is just to start from fresh. We use the current solution. We discard all what we have computed until this point, and we start the method again with the initial gets being the recently computed solutions. That's the idea. With using this, we discard the matrix V and U and construct a new matrix which is empty at the beginning of the iterations.
Okay, but at the cost of something, no, of accuracy. So
yeah. Usually, in some cases, the convergence is difficult to assess. In some cases, if the restarting is too early, the method never converts because it's never approached sufficiently close to the solution. So this is a risk in classical Krylov methods.
And can you take some evidence from the problem to decide when it is recommended to restart, or do you have, or it is not possible to get some evidence from the problem to decide in a point when it is recommended to restart the method?
Well, it's the restart, which is a good restarting value. It's very close related to the problem. For example, as I said, in our test case, the restarting was not necessary. The method converted pretty well in our examples, so very close to the LSQL. So the restarted was never in. Although the method, in fact, in our plots, we cut the iteration because the saturation, because the residual saturated very quickly. But the residual at least from our test case, is difficult to assess a recommended value for the restarted number. As I said, it's very related to the problem rather than a fixed number that works for most of the case. It's very related to the problem itself. It's very difficult to assess a value.
Yeah, because my following question was related to adaptive strategies, because I think that the main contribution is related to the quantization of the matrix. But my question is, if you think that it is possible to extend this contribution, proposing or using some kind of information from the problem to adapt the quantization of the matrix in terms of the necessities over the needs of the problem. So sometimes maybe you need more quantization or less quantization depending on the problem. What do you think that it is a good evidence to see and to extend this approach to an adaptive scenario?
Well, in fact, yes, it's a very interesting idea. In fact, our quantization or the quantization method that we used in this thesis was a pretty simple one. It's just what we are doing is generating a range of regularly divided set of values. So it's expected that for example, uniform vectors or uniform scalars are pretty well approximated by our quantization technique because the range is uniformly divided. This is a simple scheme that was selected because mostly due to its simplicity. But for example, for other distribution of matrix with some other behavior or patterns, a more sophisticated approach can be used. For example, another type of distribution for the quantization, another expression to represent the values of the quantization is a very interesting idea, and I think it's possible to define a more in ad hoc expression for the quantized matrix. The idea is just to map all the possible values of a vector into a smaller set, but how these values are distributed can be chosen for specific problems, and probably will perform much better than using this simple approach of quantization. And in fact, this or quantization approach belongs to a category called scalar quantization. There are other types of quantization. Vector quantization is another approach, which is similarly to a K-means clustering technique. So there are a lot of quantization approaches that can be used. We selected this because it's more simple, and in our case, or more general, as a general method, works pretty well. But of course, a more ad hoc routine can be constructed.
Okay, I have a last question, a last set of questions that is related to the memory consumption, memory usage, and complexity, temporal complexity. So I will start with the first question related to this issue that is on the page 34 on memory usage of your document, 34. So you are, yeah.
34.
34.
In NS LSQL?
Yeah.
Yeah.
So you declare the memory usage of NS LSQR, and then you give a closed expression, but without using asymptotic notation. This is this close expression. Could you please explain me the intuition behind this equation?
Okay, I
These are
think that
the
it's
important factors that
Yeah.
determine the memory usage in the case of NS LSQR.
I think you mean this expression, right?
Yeah, it is the same. Yeah,
Yeah.
on page 55.
Yeah. I didn't use in this case the asymptotic notation because the expression depends of several parameters that at first we do not have its specific value. For example, since the NS-LSQL is not tied to the quantized approximation, we refer as the usage of this restricted memory approximation cost as psi, just that. So this is a parameter that can vary depending on how this product is computed. We also have the values of the restarted approach, in this case the inner iteration. So we have a lot of different values that modifies the global amount. That's why I didn't use the asymptotic description, because more or less without having the specific set of values, the expression does not change too much. But the general idea here, or probably the most
the dominant factors. So the most important.
Well, I use the asymptotic notation, but the expression remains almost the same. So, sorry, this was for the memory usage. This is for the computational complexity.
Yeah.
So the general idea here is, or to gain a conclusion, is that the NS-LSQL memory usage and computational complexity depends on several factors. We can use, for example, if T out, in this case, the outer iteration of the restarting approach is 1, and T in is equal n, will give a fully without restarting n iterations of the NS-LSQL method. In this case, the complexity is similar to the LSQL version, which is around n cube, a cubic behavior of the complexity. But again, for example, if we consider that a function evaluation is very costly, maybe this expression could be greater than the quadratic or cubic expression. And in fact, in our tested, some functions are very costly to compute. So in some cases, takes much more time than other examples. So it's very dependent of the parameters and elements of each problem. But the general idea is that it depends on many factors, and depending on the cost of these factors, the complexity or the computational time and memory usage varies from one to other problem.
Yeah. It is not so easy to interpret the equation in terms of memory usage, but now it is more clear for me. So regarding the metric quantization method, you have also a memory usage and computational complexity equations on page 55.
Yeah, this one and this one, if I recall.
This is a very simple expression.
Yeah.
Can you explain me which is the intuition behind the expression of the right part of the equation?
Yeah, in this case, we have the complexity for the memory usage. The main idea here is that, well, the main conclusion that we can obtain for this expression is the memory usage is related to the number of bits. In fact, if we used 64 bits, for example, in any combination of layers and bits, we have this number equals 64, and 64 times m times n is a double precision matrix. So the memory usage is more or less obtained by, or in this case, we are considering our implementations. So our implementation ensures the usage of this number of bits, even if the computer cannot store 5 bits, for example, or data structure makes possible this usage. However, we also have some additional cost of storing, which is this part of the equation. So we have an overhead, an additional overhead of using these data structures. It's not too large if we consider that in our cases we use 4 layers. This is proportionally to storing 4 additional vectors. It's not too much, but it's an additional overhead. But the main conclusion here is that we achieve the desired rate of memory usage or compression. And for the case of the computational complexity, it also had a lot of terms, but the main conclusion here is that this is the complexity of the matrix construction. It's not too relevant because the construction of a matrix is just it's only a quantized matrix constructed only once per Levenberg-Marquardt iteration. It's not updated in each NS LSQL iteration. So this is computed just one time and then is used in NS LSQL. This is the complexity or the elemental operations for a single transpose vector product. And in this case, the conclusion here is that this part is related to the product between the quantized matrix and the vector, the quantized itself. And this is the additional cost that we paid for the decompression routine. So in this case, the conclusion here is, although the expression is very close to the of a matrix vector product, we have an additional overhead that is obtained due to the usage of the decompression routine. So the method is not purely similar to an explicitly stored matrix. It's more costly, but its cost is less than using, for example, a matrix-free approximation for the transpose of the Jacobian matrix, because we have this additional cost for decompressing the data, but it's much less than performing the several matrix transpose vector products.
Okay, Ariel, thank you very much for your answers. Now we will go with the turn of Professor Torres. Professor.
Hey, thank you. So you got most of my questions, so that's not fair. But to continue the tradition, can we go to the slide 27 and ask about B sub k tilde and B bar? It's basically or n squared memory. Yeah, just to be clear, and in this case, this is the comparison between the original algorithm, which require this symmetric property of the, or basically having the J transpose exactly. So in this case, just to be more explicit, having this approximation of J tilde on the second equation, modify basically B tilde B bar, right?
Yeah.
And now we get this order n square because we need to store more coefficients besides the vectors. And that's the part that we should control, or you need to control when this gets too large. Can you, for instance, for GMRES, having this restart, there has been studied that there is a safe point after you do a restart. So if you do it too early, you may never converge. And also in this case, if we build the complete factorization in this case, we will get to the exact solution because we're going to build the full Krylov subspace. Can you comment on this? I mean, I know we never get to restart the algorithms because they were converging too fast, which is an advantage. But in this case, if we want to get greedy, can we quantize also the B matrices as well?
It's a possibility to quantize also. It needs a further research how this will affect. For the term of the restarting, in fact, we can link maybe with GMRES because there is a relation between NS LSQL and GMRES. It's stated more clearly in the manuscript, but I have also here a small explanation of that part. Let me find it here. In fact, the NS LSQL is also a Krylov subspace method, but a different space from the traditional expected Krylov space. In fact, the matrix B sub k that is produced in NS LSQL is the same matrix that is produced in a GMRES, for example, if it's used to solve this the linear system in the equation 20. And the Krylov subspace built by GMRES for solving this problem. And NS LSQL is the space in the line 21. So we can study both methods more or less in the same manner. So if our starting value can be computed for GMRES, in this case, this restarted value can also be used in the can be used in NS LSQL. Of course, this needs more study. This is a more beige claim, but it's a link. In fact, the breakdown cases in the NS LSQL can be studied using this relation with GMRES.
Okay, thank you. Can we go to slide 34, please?
This one?
Yes. So basically, in this case, S is the shift, or is it the same for the whole matrix?
Yes and no. It's a shift, but it depends on the. Well, it's not stated here, but it's given. The expression exactly is given here. The number S depends only on the number of bits, so it's independent from the value of for a specific matrix. Its value is exactly here. The S equals this value, and so for a single layer, it's the same for all the columns. Of course, the concept of layers. It's using the concept of layers. We can use different bits for each layers. In fact, in our Levenberg-Marquardt experiments, we use 2 layers of 3 bits and 1 layer of 2 bits. So the bit does not need to be the same. Of course, the idea here is that we can approximate some part of or in some elements of the error matrix using more or less precision. That's why in this expression, here the S does not have a subindex because it's for a single quantization matrix is the same for all columns. But here it has as an I subindex because we can use another value for the bits usage in other layers. But yes, it's a shift.
Okay, so following that, can you go to slide 46?
46. This one?
Yes. So in this case, the experiment in all cases use 8 bytes, right?
Yeah.
But and we see some differences, but they are
Exactly.
more or less the same. What is better, to have 4 layers of 2 bits or 1 layer of 8 bits?
This also depends of the problem. As a general, after all the research and experiments, my general idea is that using more layers in general it's better. Of course, the idea, but this must be leveraged with the number of bits. For example, in general, the ability of using more layers have the benefit of catching some patterns, or in quotes, of the matrix. So for example, if we have a matrix that has a repeated value, using one layer we catch all that values at once. So in the second layer we approximate another possible pattern of the matrix. So in general, that's why in this case, even though we use a 1 layer of 8 bits, which is much larger value compared to the rest of layers, for example 1 or 3 or 2, it performs worse in this case, in this particular case, because we are using only 1 layer. So in general, it's recommended to try to use at least 2 or 3 layers. This can be tuned in the number of, for example, if we do not have more than 15 bits for usage, we can make some kind of combination to use 2 or 3 layers with the available number of bits. So as a recommendation, I prefer using slightly more layers than just using one big bits or big matrix of 1 layer.
Okay, so in that case, 1 second. Okay, so even though more layers will imply a higher computational cost for computing the transpose of the matrix times a vector?
Yeah. In fact, one of the reasons of this high computational time for this 32 bits quantized matrix is because in our implementation, this is just limited in our implementation, we limited the number of bits per layer to 8 bits because it's simpler to compute. So to represent a 32 bits matrix, we need to use 4 layers of 8 bits. So it adds a overhead that is proportional to the number of bits that used per layer. So we use more layers or more bits per layers, it increases the computational effort. So in general, for our experiment, it is not required to have too much bits. It's not needed. Of course, in this experiment, maybe in another problem, it's better. It's needed to use, for example, 3 layers of 8 bits or 1 layer of 16 bits. But in our cases, using a small number of bits on a small number of layers performs pretty well. So in this manner, we can control also the computational time of performing a single product of the transpose of the quantized matrix and a vector.
Right. So in this the same direction. So one option to compress a 64 double precision coefficient is to use single precision or a different kind of representation. But based on what you mentioned, you will suggest there is a research direction basically in how to use those number of bits. So as you mentioned before, 8 bits using just 1 layer will be okay, but using the same bits in 4 layer of 2 bits will be even better. So there is, you will agree that there is a way to find a better representation with a fixed number of bits than just using the default representation, for instance.
Yeah. In fact, as you said, there are some other approach of using better the number of bits. There are some representation for example, floating point numbers that points to use the bits for a problem, for a specific problem. This is used in machine learning. This is used in other numerical solvers. The idea here has the same core idea. Try to use the bits for the small number of bits that we have in a better way than, for example, a double precision that has a very large range, but maybe, for example, in our problem, the number of numbers that appears in the matrix are not too large, so we can use less bits to represent the desired number of values. So the idea is that use the bits, the small number of bits, more wisely than using a general purpose representation.
Okay, so we go to slide. We were in 50, right? That's so. I have the question about this. So, looking at the two extreme, like the blue and the purple markers, and the straight line at the beginning is using just this quantization. So, can you envision somehow kind of a hybrid solver? So, for the J transpose or the J tilde approximation, you may use, considering that you still want to spend some time in compressing and decompressing the J tilde matrix, maybe you could use certain percentage for that matrix to compute it as a matrix free, and the other part will compute it as a approximation using J tilde. Will you think that we will save some time if we do that, like having an hybrid representation?
It's a interesting option because as we seen before in the previous experiment, in some configuration we have the risk of decreasing the rate of the convergence of the method. So, for example, this is more a word claim. It needs further investigation, but in some part where the quantized matrix is not doing a good job, for example, or is not working well for the current iteration, for example, we can use pay a little more in the computational time using a matrix-free approximation, which is in general the quality of this approximation is better than the obtained through the quantized matrix. So we can improve the convergence a little bit using this matrix-free approximation. And when we are closing to the solution, we can use, for example, the quantized approximation to use for the last steps. That could be an idea. On the contrary, we can use for the later steps or the inner step. But of course, it's an interesting option to make an hybrid method. Because the idea here is to first reduce the memory usage compared to a double precision matrix, and reduce computational times compared to a matrix-free variant of the method. So as long as we remain in this portion of the 2D plot, we are in the safe place, for to say in one manner. We can move for more to the execution time, or maybe a little more of memory. But as long as we remain in this portion of the plot, the solvent can be solved more or less in a decent amount of time or memory consumption. So an hybrid mode is a pretty nice idea.
Okay, that's for me. Thank you, Ariel.
Thank you, Professor Torres. So, Professor Sauer, you have an additional question or not?
I just had one more question that arose from what Claudio was asking, and that is, so I think, Ariel, are you saying that whether 8 bits is better than 2 layers of 4 bits? Does that depend on would you say it depends on the distribution of entries in the matrix, what the probability distribution of the entries of the matrix looks like? Is that really what you think determines whether it's better to use layers than only 1 layer?
I cannot claim if that's the only element, but it is a factor that influence in the how they perform, because for example, in our, if we see some of our examples, in this case, the diagonal function is a sparse matrix. The Jacobian matrix of this function is sparse. So, for example, or even in the modified trigonometric function is dense, but the matrix has a large number of repetitive values. So in this case, we see that using 3 layers, independent of the number of bits, perform very similar. So it's some part is responsible for the distribution, but there could be another. Definitely, this some reason for the performance, but could be another reasons to why some distribution is better or some configuration is better than other.
So it's kind of an important question, and it occurs to me. It's kind of an important question to figure this out, because what it is about the matrix that makes it particularly useful to use more layers. Because if you're only using 1 layer, then these half precision compilers or quarter precision compilers that people are writing would already suffice. So it'd be interesting to find examples where your method really is better than doing just 1 layer, and try to explain that. That's of course not part of what you've done so far, but it's something you might think about in the future. So
thanks for the
yeah.
Thanks for the note.
Thank you, Professor Sauer. So if we don't have more questions, we don't have questions from the audience. So I guess that we are ready with the second part of the exam. Cristian, podemos ir ahora entonces a la calificación.
So now we turn off the streaming and we go in private mode. And Ariel went to the waiting room. Already got vaccinated?
I did, yes. Yeah, we're doing pretty well now in the US.
Yes, we're going fast.
Okay.
Hi again.
Hi, Ariel. So we are on the streaming again, and we are with you again. We have some news. The committee has a very good impression of your work in both parts. In the writing part of the document that the Commission has reviewed, it has a very good impression about your document. It has a lot of information, and it is very well explained. So in the case of the oral exam, we also have the same impression. So your work was very good, and the question part was also very good. So for the level of the master, for the master level, we think and we agree that you have a very good work, and so accordingly we graded you with the maximum note. So you have a 100 in both items. So from now you have the master in informatics degree. Congratulations, Ariel.
Thanks.
Congratulations.
Thanks.
Yeah, and thank you. This is really great work, and I'm really glad to hear about it.
Thanks. Yeah, your words are really well appreciated.
You can say some
give
words.
a speech.
You prepare a short speech. Yeah.
Yeah. Well, I'm going to make it kind of quick. I read a more extent things in the manuscript, but I know that some people, my friends, are watching the streaming. So first, of course, I want to thanks to my family. I know they are not watching the streaming because they were too nervous, but probably they will see the record later. They have supported me from a lot of years, so this was not an exception. They support me in all the decisions that I've taken. So I'm very grateful for that. Thanks to my girlfriend Renata, she supported me a lot, and especially in the master time that I've been, the time that I'm spending in the master degree, support me emotionally. Probably I wouldn't have reached this far without her help. So yeah, I'm very grateful for that, for her support. It was a very important part on all this process. Also to my friends that I'm very surprised they're watching the streaming. Yeah, they also, especially also the ones that were studying with me all those years. We suffer most in the same page, so it's kind of funny to have people in the same moment than you, suffering the same elements than you, so probably laughing on the same elements, so it makes the time more funny and more easy to progress in the program. And finally, thanks to Professor Claudio, we have been working for a lot of years now, and not only in the master degree program, but also we worked previously in my undergraduate degree phase of study. So I hope to keep in touch. I know that we still have pending the paper, but I mean more after the paper. I hope to still keep in touch after all. Have supported me from a lot of decisions in a lot of moments. So I'm very grateful for that also. And of course, thanks to Professor Mendoza and Professor Sauer, who have been watching this humble presentation. Yeah, it's also very important, especially Professor Sauers, because I've been using your material in some context when I've been making classes. So you are a very popular person in the department. So it's very special to have you here, hearing me this thesis and this presentation. So
yeah, this is my pleasure.
Thanks to all.
So I think that we are ready with your exam. So
we take a picture. We all looking at the cameras, smiling. So say cheese.
For me, it's easy to smile, so I don't think it's necessary.
Okay, very good. Thank you very much. Thank you all for your time.
Yeah, thank you. Thank you, Professor Sauer. Congratulations to Ariel. Congratulations also to the advisor, Professor Torres. And we thanks to the audience, and we will see you in brief in 2 days. We have another exam.
Yeah. So the great Daniel.
Yeah, Daniel.
Very great person.
So see you next.
Okay.
Thank you.
Thank you. Thank you, everyone.
Bye-bye.
Take care,
Thank
you all.
Mm-hmm.
Stay safe.